Hey guys, this is the 5.2 notes. This section is called bisectors and triangles. The last section we focused on perpendicular and angle bisectors. This one we're going to focus on different types of bisectors. So when three or more lines intersect at one point, then the lines are said to be concurrent. All right. And then the point of concurrency is the point where they are intersected. Okay, so where they intersect is that point of concurrency. So, right, if a bunch of lines intersect at a point, then they're concurrent, and then the point of concurrency is that point that they're intersecting at. And the point of concurrency is going to be called the circumcenter of the triangle. If I can spell it right. All right. Now, this brings us to the circumcenter theorem. Okay, so the circumcenter theorem tells us that the circumcenter of a triangle is equidistant from the vertices of the triangle. So that's our formal definition. Oh my gosh, I can't spell triangle. All right. Now, if we look at the picture to the right, we can say, right, that they're equidistant, meaning that certain lines are going to be equal to each other, knowing that there's a circumcenter. So if we look at line AP or PA, whatever one you want to name it, let's just name it PA. We'll start with P for all of them, since P is our circumcenter. And then we also have PC and then PB. So all three of these lines are going to be equal to each other by the circumcenter theorem. All right, now we're going to focus on the three types of triangles, acute triangles, obtuse, and right triangles, and we're going to look at where the circumcenter lies for these triangles. So the circumcenter can be on the inside. It can also be on the outside, or it can be on the triangle. Okay, so it could be lying on one of the lines. It could be some point outside the triangle or some point inside the triangle. For acute triangles, they are always inside. Okay, so an example right here, our circumcenter would be about here, right, with lines going through it. Right, and you'll see, right, that point of concurrency or the circumcenter, right, is inside the triangle when it's an acute triangle. Now, when we have an obtuse triangle, it's always on the outside. Okay, so our circumcenter is on the outside, right? have a line going through here, line going through here, have a line going through here. Okay. So again, acute inside, obtuse outside, and then obviously our last one, a right triangle, it's going to be on our triangle. Okay. So line going through, another line going through, and then another line going through. Okay. All right, the next definition we're going to look at focuses on creating a circle around our circumcenter. Okay, and the circumcenter of triangle ABC is the center of this circumscribed triangle. So this is the circle we're going to make around the circle's circumcenter, where that P point is exactly in the middle. But the circle needs to contain all the vertices of the polygon. So a circle that contains all the vertices of a polygon is circumscribed about the polygon. Okay, that goes right here. I just couldn't fit it. All right. All right, so let's look at some examples. All right, so we're going to start with this one. So let's call this example A, because this first box doesn't necessarily go along with this picture on the left. It has its own picture. The next 3 questions will go along with this picture up here. Okay, so this says that DG, EG, and FG are the perpendicular bisectors of triangle ABC. Find GC. Well, it says G is the circumcenter, right? And then by the circumcenter theorem, G is equidistant from the vertices of ABC, of triangle ABC. So if we look, right, we're looking for GC right here. Right? That's what we're looking for. We're given GB. Oh, right here. We're given that's 13.4. Right? So if we know, right, by the circumcenter theorem, we should know that GB is equal to our GC. Okay? And if GB is 13.4, then our GC is 13.4. Good. All right, so let's move on to example 1, which deals with this question, this question, this question, and this picture here. Okay, so it says use a diagram and find GM. So we're looking for GM. Oh, no. GM. All right. It says MZ is a perpendicular bisector of GHJ. Okay, so MZ right here is a perpendicular bisector of the total GHJ, right? So that's cuts this piece right here, GJ in half, right? So we also should know that this is going to be equal to this, right? Because it's a perpendicular bisector, it cuts those evenly. So now we know MJ is going to be congruent to GM, and we know MJ is 14.5, therefore GM is 14.5. Next one we want to find is GK. So we're looking for GK. Okay. it says KZ is a perpendicular bisector, right, of GHJ, right? So we know right here is a perpendicular bisector, right? That tells us that this piece here is congruent to this piece, right? So we know KH is going to be congruent to GK. We know KH is 18.6. Therefore, GK is 18.6. And then the last one says find JZ. Okay, JZ is right here. Right. We know Z is the circumcenter, so JZ is going to be also equal to GZ and HZ, right? Therefore, we just find one, and we can see that GZ is 19.9. Therefore, JZ also has to be 19.9. All right, now we have another definition. This definition is the in-center. So a triangle has three triangles so that it has three angle bisectors. The angle bisectors of the triangles are also concurrent, and the point of concurrency is called the in-center. Okay, so the in-center theorem tells us that the in-center of a triangle is equidistant from the sides of the triangle. Okay, so that means we're looking at all of the ones with perpendicular bisectors, and they're going to be equal to each other. So we can say XP equals YP and ZP. Okay. Now we'll look at acute, obtuse, and right triangles for the in-center. So the in-center, in this case, is always inside the triangle. Okay, so whether it's acute, obtuse, or right, they're going to be inside the triangle. If it's acute, it's going to be about here. And then we make our perpendicular bisector through it. All right, and that should go right to that corner. And then same with here. Okay, and then same with here. Okay. The obtuse ones, something like this. And then our right one would be right here. All right. All right, now let's look at a circle. Okay, so when we have an in-center, we actually have an inscribed circle, so it's inside the triangle. And it says the in-center is the center of the triangle's inscribed circle, a circle inscribed in a polygon intersects each line that contains a side of the polygon at exactly 1 point. All right, so let's look at an example. We have example 2. We have equations for QP and RP. It asks what is the radius of the circle, the inscribed circle. Okay. All right, now, all right, it says solve for x. Well, we're given that we have two bisectors, RP and QP, right? We know they're going to be equal to each other because P is the in-center. So we set QP equal to RP. So 3 times x plus 1 equal to 5x minus 3. Distribute, we get 3x plus 3 equals 5x minus 3. Okay, add the 3, subtract 3x. So we get 6 equals 2x. Divide by 2, and we get x equals 3. All right. Now we want to find the radius. So once we solve for x, we find the radius. All right. So the radius would be of this inscribed circle in here, right? So any of these bisectors would represent the radius. So we can just use RP. Right. And all we have to do is substitute in x, which we just solved for, to get that distance for RP, and that's also our radius. All right, this last problem is sort of a long one. We need to find the coordinates of the circumcenter of the triangle for ABC. The thing we need to do is solve for any two bisector equations and find out their intersection points. Okay, so what we want to do is first find the midpoint of two of the lines from ABC. Okay, so I'm going to find the midpoint. So midpoint of AB. Okay. I have the picture drawn out here. You can kind of see the midpoint of AB is right here. Right. If you need to, you can use a midpoint formula, which is just right, midpoint equals add the x's, divide by 2, comma, add the y's, divide by 2. Okay, so midpoint for AB, right, would be -3 plus 5 over 2, comma, -3 plus 1 over 2. Right, from these points right here. Right, and that reduces down to 2 over 2 or 1, and that reduces down to 2 over 2 or 1. So there's the midpoint. Now let's also find the midpoint of BC. So B is 5, 11 over 2. And then we also have 1 plus -1 over 2. Therefore, that midpoint is going to be 8, 0. All right, now we need to find the slope. Okay, our slope formula is y2 minus y1 over x2 minus x1. So find the slope. So y2 is 1 from that b's y coordinate minus -3 over 5 minus negative 3, which reduces to 1/2. Okay. Slope here would be negative 1 minus 1 over 11 minus 5, which reduces to negative 1/3, because you get negative 2 over 6, which reduces to negative 1/3. Now what we want to do is we want to find the perpendicular slope, because we have perpendicular bisectors. So, right, perpendicular slope, we get that by taking the opposite reciprocal. So opposite of 1/2 is negative 1/2, and then flip the numerator and denominator. So negative 2 over 1 or negative 2. And then same thing with here, perpendicular slope, right? This is negative 1/3, so it becomes positive 1/3. Flip the numerator and denominator, and we get 3 for that slope. All right. Now I'm going to flip the slide and finish the rest of the problem. The next step is to find the equation of the line. So find equation of the line. Right, so we need to use the formula y minus y1 equals m times x minus x1. All right, so we're going to use that midpoint. So AB's midpoint was 1, negative 1, and the midpoint of BC was 8, 0. So those are x1, y1s we're going to plug in. And then our slopes, so our perpendicular slopes, were negative 2 and positive 3. Right now we just need to solve for the equations using this formula. So y minus negative 1 equals negative 2 times x, right, because our slope is negative 2, times x minus 1. This one would be y minus 0 is equal to 3 times x minus 8. Okay, so we have y plus 1 equals negative 2x plus 2. So y is equal to negative 2x minus 1, because we subtract that 1. This one reduces to y equals 3x minus 24, right? Because the 0 cancels out, distribute the 3 to that parentheses. And now last step, sort of last step, right, is to solve for x. Right, so we're going to set them equal to each other. Set equations equal. So negative 2x minus 1 is equal to 3x minus 24. Right, that's because y equals both of those, so we can set them equal to each other. Right, so if we add the 2x over here to both sides and add 24 to this side, we get 5x equals 20. Sorry, this should be 2x plus 1 here. That's why. And then we get 1 plus 24 is 25. And then the last step, divide by 5. So x equals 5. And now finally, the last step is just plugging in x equals 5 into one of the equations that we solve for. So I'm going to use y equals negative 2x plus 1. Plug in that 5. We get y equals negative 9. So our solution finally is 5 comma negative 9. Right, that's where the circumcenter of this triangle is going to be.